Hello everyone, welcome to Medis Global. This is the final chart of the mathematics in which will include the important formulas for the complex variables and the Laplace transform. So as you can see here, these are the outlines. First one is basics, then after methods of constructing analytic function, then third one is complex integration, then after Cauchy's integration theorem, then after Morera's theorem, then after Lorentz series, and at the end we'll discuss about Laplace transform. So let's begin one by one. Here first one is complex variables. In that first topic is if z is equals to x plus iy is a complex number where x and y are real numbers called as real and imaginary part of z. So these are some basic portions we have included in the start. Modulus of absolute value is equals to mod z is equals to under root x square plus y square. Here argument of z is equals to theta, which is equals to argument of z is equals to tan inverse y by x. Then after function of a complex variable, it is a rule by means of which it is possible to find one or more complex numbers w for every value of z in certain domain D. Then w is equals to f of z, where z is equals to x plus iy. Here w is equals to f of z is equals to u of xy plus I into v of xy. Then after next topic is continuity of f of z. Before that, if you are new to Academy, then please subscribe for the upcoming videos, and the links for the previous 5 parts you can find out in the description box. So here a function w is equals to f of z is said to be continuous at z is equals to z naught if limit z tends to z0 into f of z is equals to f of z0. Here further f of z is said to be continuous in any region R of the z plane if it is continuous at every point of that region. Then also if w is equals to f of z is equals to u of xy plus I into v of xy is continuous at z is equals to z0. Then u of xy and v of xy are also continuous at x is equals to x0 and y is equals to y0. So these are some basics. Now let's move towards the next topic. Here the next topic is theorem of differentiability, the necessary and sufficient conditions for the derivative of the function f of z to exist for all values of z in region R. Here first one is dy by dx or dy by dy or dv by dx or dv by dy are continuous functions of x and y in region R. Here second point is most important for the examination. As you can see that del u by del x is equals to del v by del y and del u by del y is equals to minus del v by del x. This is known as Cauchy-Riemann equations, or you can say that CR equations. So as you all know, these equations are most useful in the examination. More than 4 to 5 times from these equations questions were asked in the examination, and 2 to 3 times these conditions were asked in the examination. So you must have to remember these Cauchy-Riemann equations. Now then after the next point is analytic functions or regular functions, or you can say that holomorphic functions. A single valued function which is defined and differentiable at each point of a domain D is said to be analytic in that domain. Then after a point at which an analytic function ceases to process a derivative is called singular point. Then after, thus if u and v are real single valued functions of x and y such that del u by del x, del v by del y, del v by del x and del v by del y are continuous throughout a region R, then CR equations we have discussed earlier in this. So these two equations, del u by del x is equals to del v by del y and del u by del y is equals to minus del v by del x, are both necessary and sufficient conditions for the f of z is equals to u plus iv to be analytic in region R. So these two conditions you have to remember for the functions to be analytic function, or you can say that regular function, or you can say that holomorphic functions. Then after, real and imaginary part u and v of the function is called conjugate function, and an analytic function possesses derivatives of all order, and these are themselves analytic. So you can keep pen and paper with you while watching this lecture, because all the formulas and concepts we are discussing here is most important for the examination. So you can note down that equations and formulas. Now let's move towards the next point. Here the next point is harmonic functions. If f of z is equals to u plus I will be an analytic function in some region of the z plane, then the CR equations are satisfied. Then after differentiating with respect to x and y respectively, we'll get del square u by del x square plus del square u by del y square is equals to 0, which is Laplace equation. Here note that for a function to be regular, the first order partial derivations of u and v must be continuous in addition to CR equations. Then mean value of any harmonic function or a circle is equal to the value of the function at the center. So in general, for harmonic functions, the Laplace equation should be satisfied, and these two notes are important for the regular function, or you can say that analytic function. Now let's move towards the next point. Here, as you can see, that methods of constructing analytic functions. First one is, if the real part of a function is given, then f dash z is equals to del u by del x minus I into del u by del y. Then after integrate with points at z and 0, so we'll get f of z is equals to integration del u by del x at z and 0 dz minus I into integration del u by del y at z and 0 into dz plus c. Similarly, in case of v of xy is known, then f dash z is equals to del of d by del x plus I into del v by del y. Then after, in the second case, if u of xy is known, then to find v of xy we have dv is equals to del v by del x into dx plus del v by del y into dy. Similarly, dv is equals to minus del u by del y into dx plus del u by del x into dy. Then integrate this equation to find v. So we will get f of z is equals to u of xy plus I into v of xy. Then after, the next case is, if a real part of the analytic function f of z is given, which is harmonic function u of xy, then f of z is equals to 2u of z by 2 and z by 2i minus u of 0 and 0. These are the three cases, or you can say that three methods of constructing analytic functions. Now this is all about the basic portions. Now the next topic is complex integration. Here line integral is equals to integration c f of z dz, where c need not to be closed path. Here f of z is equals to integrate and curve c is equals to path of integration. Then contour integral is equals to closed integration f of z dz, where if c is closed path, then if f of z is equals to u of xy plus I into v of xy and dz is equals to dx plus I dy, then you can write integration c f of z dz equals to integration c u dx minus v dy plus I into integration c v dx plus u dy. So in general, for line integration, c need not to be closed path, and for contour integral, c is necessary to be closed path. Now let's move towards the next point. Here theorem is there, f of z is analytic in a simple connected domain, then integration z0 to z1 f of z dz is equals to f of z1 minus f of z0. Here integration is independent of the path. Then after dependence on path, in general, complex line integration depends not only on the endpoints but also on the path. However, analytic function in simple connected domain is independent of path. Now here, this is the most important equation for the examination. Cauchy's integration theorem and Cauchy's integration formula will discuss after this topic. So here, first of all, if f of z is analytic in a simple connected domain D, then for every simple closed path C in D, integration c f of z dz is equals to 0. Here note that, in other words, by Cauchy's integration theorem, if f of z is analytic on a simple closed path C and everywhere inside C with no exception, not even a single point, then closed integration c f of z dz equals to 0. Then after here, if f of z is analytic within and on a closed curve, and if a is any point within c, then f of a is equals to 1 upon 2 pi I into integration c f of z dz by z minus a. Then f dash a is equals to 1 factorial upon 2 pi I into integration c f of z divided by z minus a square dz. So up to infinite you can write down. So in general, this is the final form of the Cauchy integral formula. So you must have to remember Cauchy integral theorem and Cauchy integral formulas for the examination. Now let's move towards the next topic. Then here the next topic is Morera's theorem. So if f of z is continuous in a region and integration c f of z dz is equals to 0 around every simple closed c, then f of z is analytic in that region. Then Taylor series. So this is also important for the exam. Here, if f of z is analytic inside a circle C with center at A, then for z inside C, f of z is equals to f of a plus f dash a into z minus a plus f dash a by 2 factorial into z minus a square up to infinite. So based on the Taylor series, you can remember the Maclaurin series also. You just have to put a is equals to 0 in Taylor series. Then here, this is the another form of Taylor series where z is equals to a plus h. So here f of a plus h is equals to f of a plus h into f dash a plus h square by 2 factorial into f double dash a plus up to infinite. So this is the Taylor series. Now the next topic is Lorentz series. If f of z is analytic in the ring-shaped region R bounded by two concentric circles C1 and C2 of radii R1 and R2, where R1 greater than R2, and with center at A, then for all z in R, f of z is equals to a0 plus a1 into z minus a plus a2 into z minus a square plus up to a of to z minus a raised to minus 2. So here in this series the values are coming in the minus also, where n is equals to 1 upon 2 pi I into integration f of t by t minus a raised to n plus 1 into dt. Here f of z is analytic inside the curve, then a of minus n is equals to 0, and Lorentz series reduces to Taylor series. So these are some important series you can note down. Now let's move towards the next topic. Here, as you can see that zeros of analytic function, here the value of z for which f of z is equals to 0. Here if f of z is analytic in the neighborhood of a point z is equals to a, then by Taylor's theorem we can write down like f of z is equals to a0 plus a1 into z minus a plus a2 into z minus a square up to infinite. So we can write down like f of z is n is equals to 0 to infinite into n into z minus a raised to n, where an is equals to f raised to n of a divided by n factorial. Here a0 is equals to a1 is equals to a2 up to an minus 1 is equals to 0. Then f of z is said to have a 0 of order n at z is equals to a. So you have to remember this note. Then after, here as you can see that singularities of an analytic function. A singular point of a function as the point at which function ceases to be analytic. Here first case is isolated singularity. If z is equals to a is a singularity of f of z such that f of z is analytic at each point in its neighborhood. There exists a circle with center a which has no other singularity 1. Then z is equals to a is called an isolated singularity. Then second one is removable singularity. If all the negative powers of z minus a in Lorentz series are 0, then f of z is equals to into summation of n is equals to 0 to infinite into n z minus a raised to n. Then singularity can be removed by defining f of z at z is equals to a is such a way that it becomes analytic at z is equals to a. So here limit z tends to a, f of z exists finitely, then z is equals to a is removable singularity. Then third one is essential singularity. If the numbers of negative power of z minus a in Lorentz series is infinite, then z is equals to a is called an essential singularity. Limit n tends to a, f of z does not exist in this case. Then last one is poles. Here if all the negative power of z minus a in Lorentz series after nth are missing, then the singularity at z is equals to a is called the pole of order n. Here a pole of first order is called a simple pole. So these are some basic notes you have to remember. Now let's move towards the next topic. Here this is the important topic, residue theorem. If f of z is analytic in and on a closed curve C except at a finite number of singular points within C, then integration C f of z dz is equals to 2 pi I. Here sum of the residue at the singular point within C. Then calculation of residues. Three types are there. First one is if f of x has a simple pole at z is equals to a, then here residue of f of a is equals to limit z tends to a z minus a into f of z. Then second one is if f of z is equals to phi of z divided by phi of small z, where phi of z is equals to z minus a into f of z and f of a is not equals to 0, then residue of f of a is equals to phi of a divided by phi dash of a. Then after third one is if f of z has a pole of order n at z is equals to a, then residue of f of a is equals to 1 upon n minus 1 factorial into d raised to n minus 1 divided by dz raised to n minus 1 into z minus a raised to n into f of z at z is equals to a. Here n is equals to order of singularity. Then here note that if an analytic function has singularities at a finite number of points, then the sum of residues at these points along with the infinity is 0. So these are some important cases for the residues, and calculation of residues you have to remember, because sometimes the questions may be asked like find the residue of any term, so you just have to remember these equations. Now let's move towards the next topic. Here the final topic of this lecture is Laplace Transform. Here first one is introduction. Laplace transform is a method to get generalized frequency domain representation of a continuous time signal and is generalization of CTFT, where CTFT stands for continuous time Fourier transform. Here definition of Laplace transform. Laplace of f of t is equals to f of s is equals to integration 0 to infinite e raised to minus f st into f of t dt. Here it is one-sided or unilateral Laplace transform where s is equals to sigma plus j into omega. Then Laplace of f of t is equals to f of s is equals to integration minus infinite to plus infinite e raised to minus st into f of t dt is two-sided, or you can say that bilateral Laplace transform. So these two equations are most useful in the examination because more than 2 to 3 times these equations only asked in the examination. Then here are some properties of Laplace transform. First one is frequency shift. Here Laplace of e raised to minus at into f of t is equals to f of s plus a, and Laplace of e raised to at f of t is equals to f of s minus a. Then time shift. Laplace of f of t minus t naught is equals to e raised to minus st0 into f of s. Then after differentiation in time domain, Laplace of d by dt f of t is equals to s f of s minus f of 0, where f of 0 is initial value of f of t. Then if initial conditions are 0, here differentiating in time domain is equivalent to multiplying by s in frequency domain. Similarly, this another equation is given. Then after integration in time domain, so here for this also equation you have to remember. So integration in time domain is equivalent to division by s in frequency domain if f of t is equals to 0 for t less than 0. So these are the two cases. First one is for differentiation and second one is for integration. Now let's move towards the next topic. So here, as you can see, the differentiation in frequency domain, L of f of t into t is equals to minus d into f of s by ds, and Laplace of t raised to n f of t is equals to minus 1 raised to n d raised to n divided by ds raised to n into f of s. This equation is also very important for the examination. Here differentiation in frequency domain is equals to multiplication by t in time domain, and integration in frequency domain L of f of t by t is equals to integration s to infinite f of s ds. Here integration in frequency domain is equals to division by t in time domain. So these are some important formulas for finding the Laplace transform. Then after, here the next one is initial value theorem. If f of t and its derivative f dash t are Laplace transformable, then limit t tends to 0 f of t is equals to limit s tends to infinite s into f of s. Here this theorem does not apply to the rational function f of s in which the order of the numerator polynomial is equals to or greater than order of the denominator polynomial. Then final value theorem, if f of t and its derivative f dash t are Laplace transformable, then limit t tends to infinite f of t is equals to limit s tends to 0 s into f of s. For applying the final value theorem, it is required that all the poles of s into f of s be in the left half of s plane. Poles on j omega axis also not allowed. Then after convolution theorem, here it is most useful for the examination. Laplace of f1t into f2t is equals to f1s into f2s. So these are some equations and theorem. Now let's move towards the direct Laplace transforms of the functions. Here Laplace transform of the periodic function. If f of t is periodic function with period t, then Laplace of f of t is equals to 1 upon 1 minus e raised to minus st into f1 of s, where f1 of s is equals to integration 0 to t e raised to minus st into f of t dt. Then Laplace transform of the standard functions. Here this table is most useful for the examination, because for solving any example you have to remember these standard equations of Laplace transform. Here some more equations are there, you can note down, like cos of at into u of t, then after sin of h at into u of t. So these are some standard formulas you have to remember. So yes, we have included here total 25 formulas, like f of at is equals to 1 upon mod a into f of s by a, then after e raised to minus alpha t into sin omega t is equals to omega upon s plus alpha square plus omega square. Similarly, t raised to 1 by 2 is equals to under root pi by 2s raised to 3 by t, and the last one is t raised to minus 1 by 2 is equals to under root pi by s. So these are the important formulas for the complex variables and Laplace transform, in which we have first included basics, then after methods of constructing analytic functions, then after we have seen complex integration, then after Cauchy's integration formula and theorem, then after Morera's theorem, then after Lorentz series, and at the end we have discussed about Laplace transform. So this is all about the 6th part of the mathematics. So now we have completed all the formulas for the mathematics portion, so you can check out the previous 5 parts in the description box. If you like this video, please do like and subscribe to our channel for the upcoming videos, and share this video to maximum study groups. Thank you so much. Hope for the best. Good luck.